Hi, everybody. Welcome back to Brokers Session 2. We have myself moderating today, and we have David Young, who will be in the Zoom chat and the Slack chat getting questions for us during question time. First up is Matthew Graham speaking about Babamul. Take it away.
Thanks, Melissa. Right, so I want to give an update on Babamul, which is a brokering effort that we are working on at Caltech. Some folks may remember presentations we gave at the meeting in Washington last year, where we were arguing that there are a number of misperceptions about this whole brokering environment and the brokering world. That you need a supercomputer, that you need to be connected to the fire hose, that you need to persist everything, and that you need a local copy of everything. That there are alternative architectures, alternative ways of working with this. I think a second thing that's becoming quite apparent now as we're moving in, and as we're hearing from some of the talks already this morning as well, is that we are actually in an evolving landscape. If you go back 10 years and you look at what the original ideas, architectural ideas around things like Sky Alert and VO Event for brokering in this environment, they were originally conceived to manage volume and velocity, because the concern was that we would not be able to handle millions of alerts a night and that sort of thing from transient astronomy, things that have gone bump or have moved, whatever. We now seem to be transitioning to supporting variety as well, much more, and that the systems we're talking about are actually sort of general time domain astronomy things, looking at variable sources, and not just things that have issued a 5 sigma alert. And this means that we've got new use cases in thinking what we're doing, that we need to handle light curves, SEDs as well, and not just transitioning. And these are now primary data objects. Veracity, we're not really thinking about yet, but we've had some people talking about provenance and stuff like that. So really what we need now is we need machine learning, and we also need a generic information management system. Now, you'll remember that we had cost-effective intelligence last year. We're using an edge computing architecture, and these are hardware accelerators specifically for deep learning. I demonstrated last year in one of the Corel dev boards at the team meeting that we could process about 240,000 alerts in about 5 minutes in 2019. That's come down to less than 3 minutes in 2020. So that means you can do nights of LSST alerts in roughly an hour or so. That's very fast inferencing. So if you've got a trained data learning model and you apply that, there's your inferencing. So you have one of those per classifier or whatever. We demonstrated this with the real bogus system that we use on ZTF. This is processing thumbnails and everything flowing through, just running on a Raspberry Pi, and you get the same accuracy as if it's running on a big computer. So this that takes away the requirement of supercomputing very largely. In 2020, we're now able to connect multiple TPU devices to the same Raspberry Pi. So that means we can run a different classifying inferencing algorithm on just a Raspberry Pi again. So we have there, that's 3 separate binary classifiers we could have running on a Raspberry Pi. There's also new technology. There are these new dual TPU boards which came out within the last month. So that gives you 2 of those edge things on a very small wafer, and obviously you can stack those if you have the right supporting thing. So the idea here is that this is very lightweight, very cost-effective computing. If what I need is big computing to my classifier, I can do it all on this, and I don't need the supercomputer or cluster in my basement. Another thing that we're exploring now is federated learning. So the idea here is, instead of bringing the model, we bring the model to the data rather than the data to the model. So we actually use the edge computing devices to distribute out the learning. One advantage of this method of deep learning in machine learning is it handles data privacy very well. You're not transferring data. The only thing that gets transferred across are the weights from the model, the really learned weights. So if you have access to proprietary data in your brokering system, you don't need to share that with anyone, but the benefits of that are shared by everyone because it'll improve. So specific learning across a variety of clients contributes to the global model that's centralized and distributed out in some way. There's also this idea about which models should we be using. We are very keen, obviously, with this sort of lightweight approach we're taking, that we also are interested in reusing models where possible. Deep learning can present a very high bar to the novice. You're never really certain whether you should be, what flavor of CNN or what flavor of RNN or something more exotic you should be using, and things like that. Even if you're an expert, model selection, hyperparameter optimization, using things like AutoML can be very expensive. So what do we do? Well, you want to use models that people have already trained for specific things. And TensorFlow have an initiative called TensorFlow Hub, which is an open repository of trained machine learning models. And the advantage here means that you can take an off-the-shelf model and you can use transfer learning just to adapt it to your particular case in hand. And so what we're envisaging is that there may be a slew of models that we've pre-prepared, or that the community has pre-prepared for specific astronomy problems, or maybe not so specific astronomy problems. And then we can deploy them across these federated units just to do the fine tuning to the data that we've got in hand. And that way, you know, you can take off the shelf and you're already using still your lightweight architecture, even to do the new learning. So that's the sort of machine learning, deep learning side of it. In terms of information management, which is this idea of the broker plus the Marshall plus the Tom plus the data archive. As we mentioned yesterday, we've got this new initiative coming through at Caltech and with Josh Bloom's group at Berkeley called Fritz, which is replacing all these Marshall systems that we've previously had. So it combines Kowalski, which is our internal data infrastructure based around MongoDB that we use in ZTF, and is extremely performant. I would suggest Lasserre look at that seriously as a NoSQL backend, because we found it matches queries fast. It's extremely performant. Plus a modern front looking end from Josh Bloom's Sky Portal group. And this is the sort of, you know, the way you can manage your watch list and the way you can manage your annotations, talking to telescopes downline, all that sort of thing. So that's a separate component. But the idea is that we can use the lightweight computation in the back end then, which will just plug into this. And this can be cloud deployed or it can be on-site deployed. So as I say, Fritz has a whole load of functionality into it. Take your pick, it can do it. It can, you know, there's all sorts of things, and it's already got about over 6 FTEs worth of effort in by some very serious coders, including one of the developers of SciPy. So this is a very good, and it's open source. You can pull it over, distribute it, use it to your heart's extent. So I'd encourage people to have a look at this and reuse it. So in summary, I think the volume, velocity, and now variety of time domain is presenting us with new challenges that, you know, we may be struggling to keep up with. I think we still argue that these traditional computational approaches to handle these event streams are not optimal. We can certainly do much better, particularly with these lightweight edge computing, federated learning techniques. These give us decentralized networks of very low cost components. So the buy-in is not that expensive. You know, a couple of $100 really for that sort of side of things, and some cloud time if you want to do the Kowalski deploy or the Fritz deployment as well, and reusable models, so you're not having to do all this yourself. You just use an off-the-shelf thing. So these feed state-of-the-art management systems, and the idea is that we can then manage industrial scale alert streams for processing on less than $1 a day, and this enables, you know, people running brokers or brokering systems or data management systems, talking to the alert streams from high school students up to big institutes or, you know, high level institutes. And I think this is, you know, would completely change where we are going forward into the LSST era. So I'll leave it there. Thank you.
Thanks, Matthew. Questions for Matthew?
Yeah, I've got one from Guillermo Cabrera, who's asking, how would the community use the Google Edge TPUs in times of VRO, or, and would they need to have access to the data locally?
So we've demonstrated that the streaming is sufficient. One of the models that we're looking at is 5G networks, which can easily handle even potentially the full fire hose from LSST. And there are shields that you can get for Raspberry Pi, which will enable it to have 5G capability. I mean, the Raspberry Pi is just the sort of the device in hand, but there's a huge growth market in this in terms of what's coming in terms of edge computing. So it's, you know, just what we're demonstrating as capability. And flowing, we've demonstrated with the ZTF alert stream that it just flows through in real time. There's no need to persist it or anything like that. So I think that the networking capability on that is not too difficult. There's also an idea of using smart AI to learn where alerts can be distributed in a decentralized network. And this again is what people are thinking about with the IoT sort of side of things.